Okay, so I will give this. So thanks to the SOC for inviting me to give this presentation. I will give this presentation on behalf of the SVOM team, that is a huge consortium of international labs, and with main contribution from China and from France. So SVOM stands for Space-Based Multi-Band Astronomical Variable Object Monitor. It's a mission that is supposed to be launched at the end of June this year, so pretty soon. So quite exciting time for us. And it's a mission that will last for 5 years. And what we would like to do with VOM is to study the high energy transient sky in synergy with multi-wavelengths and multi-messenger facilities, as I will show you in the next slides. So here in this diagram, you could see the time scale and various type of transients we are interested in. The primary target of the VOM is obviously GRBs, but we are also interested in the whole bunch of sources. And why we are interested in that type of sources is because these transients are related either way to the birth, destruction, or feeding through accretion of compact objects. And by studying that type of transient, we will be able to better understand GRB physics, trying to study accretion in different regimes, try to understand the physics of relativistic jets. And as you could see as well here, for the X-ray luminosity or in optical, this type of objects are really bright. So we could detect them really far away and use them as cosmologic probe to study the contents of the universe, for instance. Another important point is they are releasing a lot of energy in different form, kinetic, radiation, gravitational wave particles in their surroundings, and that will have deep implication on the evolution of their host. And by studying that type of transient, it's a way to see how compact object will act to structure matter on the large scales. So now I will come back to the almighty GRBs, the transients among the transients. So GRBs, for those of you who don't know, are signals the violent formation of a stellar mass compact object, either way a black hole or a neutron star, and the launch of relativistic jets, more or less oriented towards the Earth. We have distinction between two types of GRBs, short GRBs during less than 2 seconds, and the progenitor, we think they are due to the merger of two neutron stars, for instance. And for long GRBs, with a duration above 2 seconds, typically will be the core collapse of metal-poor massive stars. And in the process, in fact, of forming the compact object, you will have accretion, emission of relativistic jet, and within the jet, you will have some internal dissipation, and you will have the prompt emission that is characterized by a highly, very intense and brief high energy emission. So typically between a few milliseconds to a few hundreds of seconds, with typically non-thermal spectrum. We don't really understand yet what is the emitting processes of the prompt emission. Then the jet will propagate and collide to the ISM and will create a forward shock that will create by synchrotron radiation an afterglow emission. What is very interesting, if you see here a bunch of afterglow emission like obtained in visible, is the flux is decaying really fast in a short amount of time. So basically, if you want to study that type of beast, you will need various type of instrumentation to be able either to follow the very bright emission and also the late faint emission. And you have to do that if you want to characterize all the properties of the GRB population and be able to understand how they work. And that is really well explained here in this diagram, where you will have the prompt emission, all the afterglow emission from radio to gamma rays. And the thing is, here you will need some kind of shallow to try to go to that really deep understanding, you will need to more instruments with a better sensitivity. And you will need cooperation, international cooperation, to be able to follow these targets, because otherwise one mission will not be able to cover all the spectrum over all this large amount of timescales. Another important thing GRB tells us that thanks to the event that happened in August 2017, is the fact that some of them could be associated with gravitational wave event. So that is the unique event where we find everything we wanted, in fact, and we made a lot of progress in understanding GRB physics for short GRBs, for instance, where here, in fact, you could see the signal of LIGO, where you will see the coalescence of two neutron stars, and 2 seconds later, a detection by Fermi and integral of a short gamma ray burst that was off axis. So basically making this GRB very faint in terms of isotropic energy. And the fact as well, in fact, in comparison to what I showed you earlier about the afterglow emission, in fact, in here you have to wait for at least 100 days for the afterglow emission to peak in various bands from X-ray to radio before decreasing. And this event was also famous because we detected a few hours after the trigger a kilonova close to a galaxy at 40 megaparsec. And from all of this data set, from electromagnetic signal plus gravitational wave signal, we managed to perform a lot of different fundamental physics tests, but also astrophysics. So for instance, we were able to measure the Hubble constant in an independent way. And this shows all the potential of that type of joint detection between electromagnetic signal and gravitational wave in order to try to solve the tension in this parameter. For instance, we were able also to put some constraint on the speed of gravity, to have some kind of constraint studying the tidal deformability of neutron star, for instance, on the equation of state of neutron star, better understand the jet physics and the structure of this type of things, and also to try to study enrichment of the ISM with heavy materials. So really rich and complex physics, and is that type of thing we would like to do with them. So we have two space discoveries. The first one is a local universe in synergy with gravitational wave and neutrino facilities, and the high energy, the high universe, the high redshift universe, where basically we could use GRBs as cosmological probe to better put constraint on the reionization phase of the universe, start to detect the first structure of the universe, population, free stars, or the first galaxies, and so on. So to do that, we implemented a ground and a space segment. So the space segment is roughly like working like Swift is doing. So I will start with that. So éclair, which means lightning in French, will be the GRB trigger camera on board, so the equivalent of the bat on Swift. It will survey the sky, and whenever he will detect a new transient source within his field of view, in fact, he will send an alert to the ground that will be broadcasted through a VHS network antenna spread around the VOM orbit. And in the same time, we crest a slew to the platform. And the platform, in less than 5 minutes, will repoint the two narrow field instruments, MXTs, that we observe in the X-ray band between 0.2 and 10 keV, and VT observing invisible. And that will enable to refine the position of the GRB first, and second, to sample the afterglow emission. We will also have the JRM, that is a spectrometer, that will extend the characterization, the spectral characterization of the prompt emission, because éclair will just well, the upper threshold of eclair is just 150 kV like that. And if you really want to characterize the full non-thermal shape of the GRB spectrum, you need to go to MEV in the MEV range. And we will do that thanks to JRM. So on the ground segment, we will have a network of robotic telescope spread between China and Mexico. So we'll have two narrow field ground follow-up telescope, one in China, one in Mexico. And the JWAC, that is a wide field camera, that with the purpose of either way to tile the huge error boxes from gravitational wave event, or to try to find some prompt optical emission to the GRBs that will be detected by JRM and eclair. To do that type of thing, one important thing in the GRB physics is not so much to detect them. Now, in fact, is to try to build a complete sample, an homogeneous sample of sources to be able to study the GRB physics and also to use them for cosmological studies. And to do that, we need to measure their redshift. Okay, and to do that in an accurate manner, in fact, we need large facility to be able to observe quickly the SVOM GRBs in order to get a redshift. If we have the redshift, we know the energetic, and if we know the energetic, after that, that unlock everything in GRB physics, and we will be able to fully exploit the data. So to do that, we decided to have a nearly anti-solar pointing, meaning that the Earth will pass through the eclair field of view at each orbit. So that reduces slightly the duty cycle, observing duty cycle of eclair, but at the benefit of making sure that our GRB will be detected in the nighttime and easily followable by large facilities quickly. The second thing, we try to avoid the galactic plane and also bright sources in order not to lowering too much the sensitivity of eclair. And basically, in fact, we will facing the galactic pole most of the time. So here, it's an exposure map of 1 year for eclair. And thanks to this, to be honest, we will be able to survey the Virgo cluster and try to search for variability in this cluster of galaxies. Now I will go through quickly on the different features of the instruments. So starting with eclair. So it has a low energy threshold of 4 kV in comparison with 15 kV for BAT. Thanks to this low energy threshold, we hope that it will be more sensitive to a class of GRB that is rich in X-rays and try to understand what is the physics of this type of GRB with respect to the classical one. And it will be also more, we hope to be more sensitive to high redshift GRBs as well. So it's a coded mass camera, as you could see here. So here is the final instrument built and calibrated, and 2 steradians. And at IRAP, we build a detection plan here, 6,040 and 400 CDT detectors, and the electronics. And one of the main features of eclair is the fact that the electronics is working in the photon counting mode, like for XMM or Chandra, for instance, and meaning that all the detected photons will be downloaded to the ground for the analysis. And that will be quite important, especially to try to understand the structure of the background in order to search in it for transient sources. It will also implement an onboard autonomous detection algorithm, image contrast and image triggers, and will detect roughly 65 GRB per year. Coming to JRM, so is made of 3 scintillator-based gamma ray detectors installed in a triangular shape around eclair. And with JRM, that will extend the spectral energy band of eclair up to 5 MeV to have a nice coverage spectral shape of the prompt emission of GRBs. It will also detect roughly 90 GRB per year. This GRB can't be followed straight away by MXT or VT because localization is quite coarse, but all the detection will be sent on ground for follow-up with our network of robotic telescopes. Next, coming to the narrow field instrument, starting with MXT. So it's using micro-power optics, working on the techniques of the lobster eyes optics. He was supposed to be the first instrument flying with that type of optics, but we were beat by Einstein probe, unfortunately. But never mind. The most important thing to keep in mind is a very large field of view. And that will be handy because when we will slew in less than 5 minutes to repoint the platform to the position given by Eclair, in fact, in a large amount of time, of a large fraction of the case, in fact, the GRB prompt emission will be still go on. And in this case, in fact, we will continue to follow the end of the prompt emission with the MXT, extending the spectral energy band down to 0.2 keV. And that is really cool to find new feature at low energies. And it will be also handy to do some tiling of the large arrow box of gravitational wave, for instance. And I will come to that a bit later. In terms of sensitivity, is roughly 4 times less sensitive than the Swift XRT. VT now. So VT is, so the main feature of VT is the fact that it will be able to sample the flux decay of the afterglow emission in the blue and red band in a simultaneous manner. And that will be an improvement with respect to UVOT, for instance, where it's a filter wheel. So if you want to change from one filter to another. A second thing is the fact that it is also more sensitive than UVOT, 22.5 magnitude in V in 300 seconds. And that is very important, for instance, because it means that from our simulation that it will be able to detect more than 80% of Eclair GRBs and will be able to probe the dark GRBs. So it is GRBs that are dark in optical. At the moment, we don't really understand why it is like this. Either way, there could be, part of them could be high redshift GRBs, obscure GRBs, or intrinsically dim object in optical. So VT will help us to do that. In terms of the ground segment, so as I said, in fact, we will have facilities in 2 sites in China and in one ground follow-up telescope in Mexico. And the idea here is we will use the time zone difference between the various sites to be able to follow and to sample the emission of the afterglow over time. And that is quite it's quite cool, in fact. Something important about the French GFTs is the fact that we implemented, thanks to the Kagia camera that we are building at IRAP, that will have cover in near infrared, and we will be able as well to put some to compute some pseudo redshift for some of the SVOM GRBs. We also managed to secure some time with other facilities like LCO GT, that is a network, the old network of robotic telescope observing invisible. And thanks to NAOC, who purchased some time to do that during the course of the mission. And we also made sure to have some collaboration and with other network facilities in order to make sure that of more than 3/4 of our GRB will have a prompt follow-up on ground. And thanks to this, in fact, we will be able to, if there is any optical counterpart, we will be able to refine the localization down to less than 1 arcsecond in terms of accuracy, and that is what is needed for VLT, for instance, each shooter to be able to get a spectrum and be able to measure a redshift. So here is a summary of all of this. So basically from the prompt emission up to the afterglow phase, we will cover 7 decades in energy. Here you could see the time scale on which SVOM will work. So after a trigger, in fact, SVOM will start an automatic sequence that will last for 1 day. Okay, and after that, if we want to follow a bit more the GRB, that will be done through uploading TOs, like for Swift. So if I summarize, in fact, and make a comparison with Swift, Fermi, and SVOM, in fact, in terms of prompt, afterglow, and here is redshift, basically we will do very, very good with respect to the existing mission, and we will improve the fraction of GRB with a measure redshift. And that is the most important thing. And at the end of the mission, we will be able to have an homogeneous sample to work with. So something important about SVOM is to try to work in synergy with gravitational wave detector, for instance. So here I took the example of GRB 170817 to show what could be the capability of detection of eclair and JRM, for instance, depending on the off-axis angle of the GRB with respect to the optical axis of eclair. So it will have been nicely detected, and in this case we will have a prompt slew to the target, and we will have been able to start observing in X-ray and in optical. And thanks to this, in fact, we will have detected nothing in X-rays because of the fact that the afterglow rise and peak at later time, but we will have certainly detected the kilonova. And even in the case where we will not have detected it, in fact, thanks to our ground segment, we will have been able to alert the GWAC to be able to do some tiling of the gravitational wave error contours to try to trigger our GFTs. But this time, because they are narrow field instrument, to narrow down to specific targets, because we know the redshift of the gravitational wave, and we will have been able to upload some MXT TOs to pave the error box. So here is a comparison of the field of view of XRT with respect to MXT. So I will go through very quickly here. So the idea, in fact, apart doing GRB science, SVOM will be also an observatory open to the community, for instance. So if you want to apply, you will be able to do that. But the only condition is you will have to include in your proposal one of the SVOM members, because he will be responsible to analyze, reduce, and analyze the data. We will also implement target of opportunity, like for Swift, on 3 different levels: normal TOs that will be uploaded in less than 1 day, and urgent TO, like for exceptional event, or for multi-messenger follow-up in less than 12 hours. And as you could see here, the fraction of the time devoted in the various programs, where at the beginning we will focus more on the GRB physics, and over time, in fact, we will relax the constraint to try to broaden the type of science we could do with the mission. And I will nearly finish. And yeah, in terms of data policies, that could interest some people who would like to use SVOM data. So the raw data and the data reduction pipeline will not be released to the public. That is a decision that has been made at the beginning of the discussion with the Chinese. But what we will provide is, for the GRB part, all the real-time VHF scientific product will be released straight away to enable follow-ups by the community. And 6 months after the GRB, in fact, we will release all the refined scientific products for people to work on our GRBs. For the general program, in fact, as I said, in fact, you will be able to propose stuff and we will have evaluation through attack. And we expect to have 1 year proprietary data period for people asking and proposing stuff. And for the basically for the TO, all the data will be public straight away, like it is done for Swift, in order to increase the follow-up and also the science that could be done through this programming scheme. And I will finish on this. That is my conclusion. So all the instrument has been implemented on the platform, on the satellites. All the environmental test has been done. Everything is fine and working nicely. In January this year, we received the go to from China and the Chinese and French Space Agency. We are go for the launch, and here you could see all the 4 instruments on the platform. And I leave you with my other conclusion. Thank you.
We have time for one very quick question.
Hi, it's Matt Page. Is the platform stable to sub-arc second, or are you taking very fast exposures with the visible camera?
Okay, I have to say that. The thing is, when we discuss this, because the Chinese are providing the platform, and when we discuss about the science requirement about this, they say they will be able to have the same type of stability of the platform as for Swift. And telling us nothing more than this. So because somehow it was like for Swift, in fact, because at the launch of Swift, in fact, we didn't know, in fact, whether or not the platform will have exactly the requested performances, because part of it was done in it was a bit secret because it was done for military purposes. In China, it's the same thing. So they will not discuss this in more detail with us. We will see when the SVOM will be launched.
Okay, let's thank Olivier again.